Hi, Leva. We are there, and you can tell us when to start.
Of course. Hi, Prof. Of
Hey,
course.
yeah. So we are here.
I,
You tell us when to start. Yeah, you can
of
start
course.
and yeah,
Of course. I probably wouldn't do the lengthy introduction that we did in the first section,
yeah. You
but
can make it shorter. Yeah.
okay. But thank
Yeah,
you so
make it very short. Yeah.
No, we'll do. No, thank you everyone for joining the second session of the data analytics. And today we have the privilege of having Dr. Priya Hassan, as well as Professor Najam from India. I gave a very lengthy introduction in the first session, but these are very well established colleagues within the society, and today they will be addressing statistical analysis for today's for this course, right? So over to you, Professor and Dr. Hassan.
Good evening, good morning. It could be anything for people around the world. I'm Najam Hassan.
Yeah. Hello, I'm Priya, and be happy to be with you all in this session in this course. Hope you enjoy yourselves. We are looking forward to this. Bye bye.
So we will start up from very fundamentals, but we'll go through it very fast because there could be few who are not familiar with Python. And essentially, the idea is this: astronomy over the years has become a data-rich science, and hence it has become essential to use uh, computers and statistics to analyze and data and make science cases with it. So what we'll do is to walk you through how we use what are the essential statistical tools which we require and how do we do it in Python. The reason for choosing Python is Python over the years has become a very successful language. It's growing. Many modules have been developed for astronomers, and hence we feel that it's a very good programming language uh, where where you can handle large data sets and make uh, science out of it. So we'll start off with some very basics of Python. You have cells of these kinds. This is a Jupyter notebook. So it depends on the individual's preference to use Spider or Numpy, PyCharm, or whichever environment you require, which suits you the best. But we will be using Jupyter Notebook because we feel it's a very convenient way of making notes, distributing it, and even running the code as we proceed. So some very basic concepts of Python. One thing, Python is case sensitive. If you declare a variable a with a small a and or with a capital one, these are two different variables. And to execute a cell, you have to press Shift Enter, or you have to execute it by this arrow on top. And as you notice here, if I say if I say A, then A small a is 23, while capital A is 56. Okay. And then these cells can act simply as a calculator. I can do computations like A plus B, or sorry, there's no B there. A plus capital A, we are getting 23 plus 56, which is 79. Or we can have A to the power of capital A, which gives you a very big number. And what I'm trying to show is the numbers which we don't have to declare these variables as we use it, like we do it in C. So here's a lot of flexibility, and even the size of these integers we define and use can be extremely large, right? So in moments, you can do things like 456 to the power of 67, and you see the numbers right there. Okay. So these can be exhaustively long, and we can do. So addition, multiplication, subtraction, division, modular division, all these things work fine. Okay. So now that we realize that, further, you can even declare, say, a variable as a complex number. You can do complex computations too. A plus 3j is one complex number, and I can define C as 4 plus 8j. We don't use I, the common one. We use j here. And when I do B plus C, addition of these complex numbers, you get 6 plus 11j, and you can do multiplications and find the real part of it or imaginary part and so on. So there are various data types which are stored in. You have integers, you have floats, you have strings, and so on. And we can define lists by, say, I can have list. I declare it as in square brackets as 23, 67, 78, 90, 3, and I can declare a list of this kind. And these are all integers as you see it. And I can have another list which can be made up of not the same data types. You can have numbers, you can have strings, and so on, and so on. Answer and right, so you can define. Sorry, yeah. So you can define lists of these kinds and use it. Okay. So now realizing this, we could probably try to do, say, sine of a certain number, 78, and we would expect
Oh, pay for
that
meeting
Python.
and I can see Lani.
I can hear some sound. So when I'm saying sine of 78, I'm getting an error, right? Because it doesn't understand what sine is. So what we have to do is, there are various libraries or modules in Python. I can import this. I can hear somebody speak.
Moses.
Yeah, so I can import math. Can you hear? Import. I can say import math. And once I've imported math, I can use math.sine. And now when I try to run this, I'll see that I'm getting an answer to that. Okay. So, and in math, if we do math dot and put a tab, you will see that there are a host of functions which are defined in the math module, and you can use any of these: exponential, sine, floor, and so on. The list is pretty large. So all these are functions which are defined within. So once I've imported math, it gets. And now when I say math dot sine, and when I run math.sine, there's somebody speaking there.
See if you are this thing.
Huh?
I am not. So I can.
Okay, so when I say math.sine, then I'm getting an answer, right? So once I have defined import math, then with math dot cos or math dot you will be able to run it, right? But very often what is done in Python is we import math as you give an alias. Say import math
Hey,
as
my
M,
number all Galileo.
and then you can, instead of writing math, math
Beyond the
all the
Kilani?
time, I can write m dot sign, and this would work again. Okay, so now you don't have to do that.
Yo
And
problem
this is
nango
the
je yo tulu kutula ko
structure which
kadzila
we
nde
often
data
use.
tadzilong sha tula kadzila ne
Okay.
data ti no afai tilong.
So here we are. Similarly, it goes on, and uh, we can do some basic mathematics here. Like for example, I define list data equal to square bracket 23, 67, 89, 78. Okay, and I'm defining data as this, and when I do sum data, I'm getting the sum of these, the whole list, 23 plus 67 plus 87, and so on. And the length of the data, if I take then it shows me that there are four integers there, 1, 2, yeah, 1, 2, 3, 4, right? And I can find the average, the mean of this as, suppose I call this mean. I do sum of data divided by len of this data, and when I print mean, I can see the value what is stored in mean by writing mean and running it, 64.5. Or we can use the function print, and I write mean, and I get the answer, right? So either you write, just give the variable name and it gives, and press shift enter, or write print mean, and you are getting it, right? So this is one way of doing statistics. And whenever you have a host of data, a lot of data, then you have to use statistics to understand, make sense out of it. For example, now I'm declaring another list where you have 12, 15, 14, so on. This is, I'm calling it data 1, and shift enter. And when I'm printing it, the whole thing is coming out, right? Similarly, you can do the same thing, sum and length, and I um, length, and then I run them. What happened here? Sum data 1 is 139. Okay, yeah, the mistake is this. The variable name was small m with mean here. Yeah, so now when I run it, I get the answer, right? The variable I declared was with capital mean, MEAN. Hence, when I am printing it out here, I have to write the same with capital. This shows that it is case sensitive. Okay, so notice the difference between this print statement, and this print statement, right? This print is, you are giving a formatted mean. In inverted commas, I'm writing mean equal to, and in flower brackets, I'm writing the variable name, and inverted commas close. And when I run it, then the answer comes out as mean equal to whatever it is. And if I had just given without the format how it has to appear, it just gives you the value. Okay. So this is, you are doing statistics by built-in functions like sum is there, len is there, and there are many functions there. But there are other modules, built-in modules, So here I'll give you an example of how we can use statistics module to do statistics. So I import statistics as stats, okay, and then I run, say, stats dot mean, and I give that variable, that list name data1, and it will giving me mean of it, right? So we don't have to find the sum and find the length of it and divide it and do it. In statistics module, you have uh, we have various functions like mean, median, and variance, and so on. And I'm using this. So I have written import statistics as stats, and I'm running it. I could have as well written import stats as S, and then I wouldn't have to write stats all the time. I can just say um, mean equal to uh, S dot mean and whatever list I'm giving, and run it. And you can notice that I get the answer even this way, right? So this is the constructs imports statistics as an alias name, stats, or import stats as whatever, and then you do it. Similarly, now you realize you can even do, say, stats dot median and data1, and when I run it, I get the median of it, and stats dot variance of the data, it is giving you variance. So variance is a measure of uh, dispersion, where basically you find the mean and you take deviations from the mean and you find the average of that and find the, yeah, so that gives you the variance. And if you take the root of it, you get standard deviation. So now the question would be that how do we know that we have to write variance here? Uh, I could have probably thought that it should be stats.var, and I run this with data1 and it should run, but you will notice that it's going to give us an error, because here we are expected to write the variance rather than var, right? So now the question is, how would I know? One thing is you can always Google search and find out what to do. Or the other possibility is you probably guess it should be variance, should be var something, and you can type a few words, then use the tab, and tab will show you that it is variance. So once you have got it, you can in the round bracket give the input, and you get the variance. Okay, you are getting the variance of it. So similarly, if I have to find standard deviation and and standard deviation I want to find, I'm storing it in stand dev, and I stats dot, and I don't know what standard deviation I have to have. So I put S and put a tab, and it gives me SQRT, stats, STDV, and yeah, so this is the one, standard deviation. And right, so you can very easily find out what function name it is. And once you run it, and you can standard deviation, and you get what the answer is. Yeah, standard deviation is the root of this variance. Okay, so this is a very easy way of doing some basic statistics. And the stats pack module has many other things which you can do. So I have a block here which gives you mean, median, mode for this data one right away. And we are printing it. And we are printing it here in the formatted way. I have changed the variable names. And okay. Okay, and I run it and I get answer mean equal to 13.9, median is 14.0, and mode is right. So this needn't be a colon. You can, whatever you write, if you put the equality sign here, then it will, in the answer it will print with the equality sign here. Okay. So you can make your output look more beautiful and easy to understand rather than just have all the. So, right. So in one print statement, we are printing mean, median, mode, all separated by these commas. So print round bracket, since we want mean equal to be written median equal to, we are putting F, inverted commas begin and inverted commas close, and in that we write these things. Okay. So similarly, we can do the measures of dispersion, variance and standard deviation, and printing it for data. Yeah, data one. We have two variables. One is data, one is data one. So I can run it with this, and I'm getting variance and standard deviation. So other way of doing it is by using Numpy. Numpy is a very good module which is used extensively in our work. And again, I am declaring some list called marks, and I've randomly put some numbers 23, 56, 45, 34, so on. So as you notice, there are hardly some 10, 15 entries there. But when you just look at numbers, you don't make sense of what's happening. So when you sort them out in ascending order, descending order, or you find the mean, median, mode, you find variance, standard deviation, then you understand the data better. Right? So that's the basic thing, statistics, where you use the descriptive statistics, where you have used measures of central tendency, use dispersion. And if your standard deviation or variance is small, then we realize that mean is a good representative of the data. And if the variance is large, then you realize that the data is scattered much more around the mean, right? So I've defined another set of, say, some marks of some students, and you say print marks, it's recreating the same thing. And now I import numpy as np, right? Import numpy as np, and I'll add some. And when I say np, right, so I'm importing numpy as np so that I don't have to write numpy.mean all the time. I can just say np.mean, and right, and I'm putting in this marks in the bracket. So when I do np.mean, I'm getting the mean of all these numbers, right? So the whole thing is extremely simple. And similarly, np.median, if I do, I get the median of it. And in this case, it is np.var, right? When we are using statistics package, then we have to write variance for the function to find variance. But here var is good enough, right? So here, if you write variance, then you may surely have issues. Okay. Then again, how do we realize what do we do? you can just say np.va and put a tab, and you will see there's vendor and where. So this is the most likely one for variance. And when I put where and marks, you will get the variance of it. And similarly, this NumPy also has sine and cosine and a lot of functions defined. So and NumPy is basically that pi is for Python and num is for numerical computation. So a lot of numerical work can be done through that, and hence you require a lot of mathematical functions to do that. So again, when you say np dot and press the tab button, you can see all the functions which are available in that module, right? Arc, sine, arctan to yeah, these are just the list with A's. Then it goes into B's, Boolean, and so on, and you have C's and so on. The list is pretty large. There are a lot of functions which are defined. There's a lot of work you can do. For example, histogram, bin size, his split, histogram, right? You can see histogram. So there are various things which we should will be using as we proceed, and whatever we require, we will use it. So, for example, I say histogram, and I say data, no marks, yeah, marks, and we are getting this area, right? So it's showing how one and which are the different ones. Okay. So now I'll show you how to create more data. Suppose I want to randomly create 1,000 data points where they are normally distributed. Yeah? So when you have data, you see how the data is distributed in the system. So there are different ways. Either the data can be distributed very evenly. It's a perfect bell shape, which is also called normal distribution or Gaussian distribution. So it's a perfect bell, symmetric bell shape, where the peak comes where the mean, median, and mode, they all are the same, right? So data which is normally distributed, mean, median, and mode are the same. So you get the peak at the middlemost value, which is the median, and that's also the average, the mean. And mode is the most frequently occurring value, right? So we are creating NumPy in NP. I'm creating random numbers, and the mean is 35 and its variance is 2, and I'm taking 1,000 points in that. Okay. So I'm storing it in the variable ages. Okay. So when I execute it, and then when I print this, you will see I have 1,000 values here, and the average of that will be somewhere close to 35. It should be around 35 because we have constructed that. And the variance of this data is 2. So the squares of the deviations, the average of that, the root of that is 2, right? So if I take, so now that I have created so many, and again you notice that they are when you have numbers flashed at you, you can't make sense of it. But when you plot it, when you find the mean, median, reduce, then you can make more sense of that. So in NumPy, also there is a function called mean define, median define, and so on. And np dot mean ages, it is giving me the mean age given here. And np.median also gives me the median and so on. Okay, so this is for the data. And similarly, you can construct randomly distributed by various distributions. We'll see how we can invoke different distributions. And if you are unhappy about ages being 35.8577776823, then I can define, say, now I'll say ages, I'll write it with the smaller ages, and I have np dot random, and again I'm using, say, normal distribution, and this time suppose I want the mean should be somewhere around 78 and variance to be 5, and I want suppose 100 values, and I use as type integer, and right, so as type integer, then now when I print these ages, which I have defined with the small a, you see that I am getting it in as integers, right? So you have dot as type int, which will give you these things. Or you can also make it a floating point number and to the second decimal place, or whichever you require. So now that you have this, I can do for this ages, I can do an np dot mean of ages, and you are getting, very close to the 78 as we had got it. And I can find np dot var of ages, and yeah, I'm getting the variance of it. Okay. So this way you can, when you create random numbers, you can even give an underlying distribution. You needn't give any distribution, but if you want specifically Bernoulli distribution or binomial distribution or normal distribution, yeah, then we can specify np dot random dot normal, and you specify what should be the mean, what is the variance, and how many points do you require, right? And if you further want it specifically as integers or decimals to the second decimal place, I can do that. So this is yet another way of doing statistics, and we will do one more method, which Priya ma'am will be working more on that, using pandas. Okay, and before we proceed ahead, for the people who have not used Jupyter Notebook earlier, you notice that a cell can either be treated made a code. This is where you write the code and execute it, or you can make it a markdown, right? So once you choose it as markdown, whatever we write here, it will appear as, it will just come as printed text matter. So the third method which we are using is pandas, using pandas. And you see it is, when I press shift enter, there was nothing to execute. It has come out as a markup language. Coming back to this, and if I put a hash sign here and I press enter, it comes out as a big one. And further, if I suppose I put two hash marks and say statistics with pandas, and you see with one hash mark it has come really big, the second one is slightly smaller. So sections, subsections, and you can keep changing it. And further, if I put yet another 3 of these, statistics with pandas and basics of statistics. Statistics. You see that the size keeps decreasing, right? So you can put these things, and further you will realize that you can even write equations here and so on. For example, I put a dollar mark and I say y uh, equal to 5x to the power of 3 plus 9, and you will see that it is coming out as a x to the power of 3 and 9. Okay. And further, in this markup language, we can even have, say, dollar, and I say alpha slash alpha plus slash beta equal to slash gamma, and press enter. I can get alpha, beta, gamma. In fact, you can get all the math functions and various things. For example, I can have, instead of plus, I can have slash o dot, right? Oh, there's a gap here. So, yeah, so alpha o dot star equal to gamma. So you can get a lot of math symbols, uh, tensor multiplication, uh, uh, and various to the power of subscript, suffix, all those things can be done. All the LaTeX commands can be run in this markup cell. And this is used basically to create notes and details, right? So now I'm doing the same thing with pandas. Yes, so yeah, so I'll make a markup, my markdown thing, and with pandas. Oh, sorry. I have to make it a markdown one so that it, yeah. So now we import pandas as PD, and I can convert these ages into a pandas data frame. So I'm calling that, say, my data pd.data frame ages. So I'm converting it into my data frame. And data frame are basically used to create tables which can have multiple columns and multiple rows. And each column can be of a different data type. For example, you can have names of objects of star clusters, NGC 1860, NGC 2348, and so on. So one column with the names, other one with their positions, RA and declination, third with their parallaxes, and fourth, and so on. So you can create multiple, and each column can be of a different data type. So here I am printing this uh, my data, and here it is. You could have also seen the table by just saying my data. Okay. So right. So this is the table. Either you print my data or you say my data. And so if you notice there are 1,000 values, so all of them can't appear here. So it is showing the first 5 rows and the last 5 rows. So instead, if you want to see only the first first 5 rows, then you use the command head. So by default, it will give you on the first. So when you say my data dot head, it will give you the first 5 rows. And if I can specify, say I want first 12, so my data dot head 12, it is giving me the first 12 rows. Similarly, there's a command called tail, a function called tail. And if I don't put any number here, it will give you the last 5 of the data from the table, 995 up to 999. And you can specify if you want from the bottom only the last 2 rows or last 3 rows, you can just see the last 2 rows. Okay, so you have the variable that my data dot tail from the data frame, right? So you can do it. And yeah, this is just an example where it showed how you can create these ages and round it up to the second decimal places, right? So here I've created where we have only up to second decimal places. Okay, so now coming to this, where we'll do a little bit of plotting. See, for example, we have import numpy as np, import pandas as pd, and import matplotlib.pyplot as plt. And from scipy, import stats, right? So scipy is again scientific Python. Right? That also has a package called stats within scipy. And through this also you can do statistics. So now I'll very briefly show if you want to plot a function of this kind, y equal to 2x squared plus 5. I define a variable x, which is np.linspace. There is one function called linspace in Numpy, and I'm going from -20 to +20, and I'm taking 100 values between them, right? So when I execute this and see, I'm seeing I'm getting 100 values, right? Suppose I had just taken 10 of these, you will see that there are 10 of them. They are equally spaced, starting from -20, ending at 20. Okay. Then I define y equal to 2x squared. Square to the power is star 2 plus 5. And I get y equal to these 10 values. And then I do plt.plot x comma y, and that is giving me the plot. So now you will see that there were only 10 points. That's why it is coming between every 2 points. It is coming with a straight line. Yeah, so somebody writes, I'm confused between what is Python and Jupyter. Python is a programming language like Fortran and C and Java and C Sharp. These are all programming languages. While Jupyter Notebook is an environment where you can run this code from a Python program. Okay. And you can do programming in Python, but what we are doing is at the moment we are using already inbuilt functions within it. So, and we are using it directly. So the difference is Jupyter Notebook is the environment. This notebook which I have opened up is the environment in which we do it, while Python is a scripting language. And the good thing of Python is it's a scripting language. You don't have to run it through a compiler. Like in C, you write the code in a certain format, then you compile it and you run the output of that compiler is the executable file which you run it. Here you don't compile it. The script which you write is what it runs, right? So Python is the language. Jupyter is just an environment. Jupyter Notebook is just a notebook. It's an environment where you can save these. You are writing comments and you are saying what this section is, that, right? And these are the commands which Python runs. So these can be run in other environments too. For example, I will say start Spider. Yeah, the Spider is another environment in which um, you can run it. So this is taking a while to start, but you can do the programming of Python, run the code even in the other environment. Okay, so I hope it's clear now. So now if to make the graph smooth, I can use this linspy with more values, and when we run it, you will see that when you run it, you'll see that it is a much smoother curve. Okay. So now we go into more of statistics, and I'm creating some data points. Say with 500 entries, I'm creating a Numpy array which has ages, income, score, and category, right? So I'm using np normal distribution with, say, its mean as 35, variance is 10, and I'm taking 500 points, and I'm taking as type as integer. Okay. Then I'm taking income random normal, also integer, and I'm taking scores from 0 to 100. Again, I'm taking 500 of them. I don't want to have any missing. And randomly, I'm giving some category, A, B, C, D categories, and again 5. So when I run this one and I create this data frame, and see, I've created this kind of a table where you have age, income, score, and category, and I can very easily run these commands. I'm using the Numpy. In Pandas again, the data frame which I have defined as df, I can do df dot mean, df dot mode, and so on. And you can see that I can get for the average mean in this data is 34.54. The median age is 35 point this, and mode is so and so, right? And the commands which I used are this df dot age mean, df age median, right? df age mode or df age median, whatever you write. Okay. And you can do it. Similarly, you can find the variance of these in data frame in square brackets for the age one. What's the variance? Okay. And this dot 2f says to give the output up to the second decimal place. So we are rounding up all the standard deviations and so on up to the second decimal place. So now we have also calculated something called interquartile range. So what are these? Basically, what we have seen is if you have data and if you arrange it in an ascending order and you plot the distribution, okay, the middlemost value of the distribution is called the median. Mean is you add up all the values and divide by number of values you have. That is the mean. Median is the middlemost value. So when you have the data distributed, the middle point of the data is called the median. And mode is the most frequently occurring value. Okay. So, right. So, yeah. So, median is also called Q2, second quartile. The first quartile is 25% of the data lies within the first quartile. 50% of the data, which is the middle point, is the second quartile, which is median. And the third quartile is the 75% of data lies within it. Okay. So Q1, Q2, Q3. Q2 is same as the median. And Q1 minus Q3 is the quartile range. And these quartile ranges are used to define, which are used to see how the data is spread out. And it is very useful to find out what the outliers are. So suppose you have data, if you have marks of people which are, say, most people have got it around 85, 85, 87, 82, 83, 85. Some are 78, one or two are 88, 89. But certainly if there's one person who has done extremely bad, say suppose he or she gets 5%, suddenly the mean of the whole data can be shifted tremendously by one bad value, right? And that person appears to be an outlier. He doesn't seem to be lying within the basic weight marks are representing the class. There's one extreme value, or one extreme value which is, say, 99 or 100% he or she has got. So suddenly these are outliers. So to define what the outliers are, we use this interquartile range. So from Q1, you subtract 1.5 interquartile range. Interquartile range is Q3 minus Q1. So Q1 minus 1.5 interquartile range will give you the limit. Any point lying beyond that is taken as an outlier. And you take Q3 plus 1.5 interquartile range, and anything lying beyond that gives you the interquartile range. So this is what you get, and we are getting a comprehensive statistical summary, and we have time is up here.
Yeah.
And we will be sharing with you this these files, and here you have a block of data visualizing for statistics. So apart from finding the centers of central tendency and this measures of variance, measures of central tendency, measures of variance, you can even do plotting of the data and see which explains the data better. So for example, I have plotted the data here, and you see this is a graphical representation of that, where this is the middlemost value. And what I was telling you about are the outliers. Outliers which lie beyond these points are called outliers. These are called the box plot. So this gives you the mean of it. This gives you the Q1 and Q2. And these are the whiskers of these box plots, where anything lying beyond this. So this length is from Q1, you subtract 1.5, the interquartile range. That is Q3 minus Q1. And 1.5 of that you subtract from this, and you get the limit of this. So anything which lies beyond this point will be an outlier, and anything lying beyond this point, this is Q3 into 1.5, Q3 plus 1.5 into the interquartile range, right? So these are various things. We will be doing it in the next class. Some we'll do a bit of statistics in that, where we'll do correlations, regressions, and so on. And as of now, you can see that we have data from DF, and I use the box plot command, and I'm doing the box plot for the incomes or whichever one, right? And I get these kind of box plots, and it gives you a very good idea of how the data is distributed, what is the mean. And so if the deviations are small, then the quartile ranges are squeezed out. If the data, the dispersion is large, then so the Q1, Q2, Q3 are measures of how the data is distributed uh, around the mean value. Okay, so with this I will stop, and now Priya will continue, and we will do a little bit of statistics next time, and we'll do it with astronomy data rather than data which we have generated here, generic type of data. Okay, thank you.
Yeah, so thank you, and I'll proceed with my thing. So I'm sorry there'll be a slight overlap between what we are doing, but let's hope that's fine. So So, Sir has already spoken to you about these different data types. I'm sure you did it last time too. There are what are called lists, dictionaries, Numpy arrays, and Pandas data frames, right? So today you have basically we covered more of Numpy arrays and Pandas data frames, right? So what you basically see is that obviously this is the syntax in which you describe a list, a dictionary, a Numpy array, and a Pandas data frame. Now, what we need to do is we need to actually see what are these different data types and when do we use which, right? For example, a list, is only one dimensional, a list of numbers or whatever. And in this, it is the indexing is integer wise, and your data type can be mixed, right? For example, you can have a string and a float and an integer, it is allowed. The next type we already spoke about last time, I'm sure you spoke about it, is dictionary, right? So, for example, you have your name, and along with that, you have your age and your where do you work and which department are you in, etc. So, that will all cover like a dictionary, right? Again, here we have mixed kind of parts. But today you have seen what are called NumPy arrays. NumPy arrays, one of the most important features about it is that you have to have a single uniform type, okay, for the NumPy array, okay. And because of that, what happens is that the NumPy array can be n dimensional, right? Like so, like a matrix. You can write a matrix as a NumPy array. It can be even an n dimensional matrix, and that will also be a NumPy array. And so therefore what happens is there are certain things in which NumPy arrays are very useful. Basically, it basically means that you can do all kinds of numerical operations on it. Okay. Now what happens is on NumPy array, on NumPy, there was another data type defined as, which is called a Pandas data frame. Okay. Now Pandas data frame is one of the most important and useful data types when we are dealing with data. Okay. Why is it like that? Because in a data frame, you basically it's tabular data. Okay, it's two-dimensional tabular data. So you have columns and you have rows. Okay, and the other thing about it is that I hope you all can see it. Nah? Can you see it or no? Can you just monitor what's on in that?
Yeah.
1 minute. You can see it. Yeah. No, can they see what I'm showing?
Yes, you can see.
No,
Make it
yeah.
bigger.
Okay, fine. Okay, yeah. So what happens is often, especially when we are going to talk about some pandas with astronomy today, so you'll see that often when we have data in astronomy, for example, say you have a catalog of galaxies, okay? So you will have their coordinates, which is RA and DEC, and then maybe you have a column which describes the morphological type, for example, stating whether it's elliptical, spiral, or whatever kind of galaxy it is. So that would then be a string, right? The name of the galaxy will also be a string, right? But the coordinates will be floats, which is your array and dec. There could be also something which could be an integer thing. So what happens often in astronomy, we use our data sets actually are in the format of a pandas data frame, right? The other important thing you need to know about this is that if and when required, you can always convert a NumPy array into a data frame, right? So that if you want to use any pandas functions, then you can convert your NumPy array to a pandas data frame. Now, the next class, that is next Wednesday, we will be covering data visualization. And basically, by that, we mean plotting tools. And basically, there are two, rather three we will cover. One is called matplotlib, then there is Seaborn, and there is Plotly. Okay, so matplotlib is the very basic plotting package in Python, and for that your data has to be in the format of a NumPy array. Okay, so when your data is in the format of a NumPy array, you can plot it with matplotlib. The other function, which is based on matplotlib, it's called Seaborn. For Seaborn, what happens is your data has to be in the form of a pandas data frame, right? And therefore, what happens is that often it could also be that maybe you do your operations as a NumPy array, but then when you want to plot it, Seaborn has some more features compared to matplotlib. It has been built on matplotlib. So you may then want to plot it with Seaborn. Then you'll have to convert your data type to a data frame. So what happens is you can convert it back and forth depending upon your requirement, right? So that's what we need to remember, that you could have different data types. You can convert one from the other, right? And depending upon the kind of packages you're going to use, you may opt for a certain data type. But in Python coding, there's nothing like right or wrong. Okay, it is more of what are you comfortable with, what are what do you find more easier, right? So if you feel that your operations work better with a NumPy array, you can use that or a whatever. So often it is just a question of choice. You see what is it that you like and you use that yourself, right? So there is no hard and fast rule. Okay, so we'll now go on to talking about pandas, and which is going to be our focus, right? Yeah. So if you see that the pandas, this thing, when we come on to it, with pandas, what we do is when we download any data, for example, astronomy data, the simplest thing we do is what is called data wrangling. That means you are actually studying the data, right? So what do we do if I give you a certain data set? The first data set, the first thing you do is you inspect your data, right? So you inspect your data with some basic operations, right? So you may, for example, do some basic stats. You may profile it, right? You may actually see, for example, in your data, are there some missing values, right? Or are there something which some outliers or things like that? That is your data inspection. You check in what is your mean median mode, for example, what are your quartiles, what is your distribution like. That is basically what we call data, what do you call, this is data, when you're basically inspecting, no, not data, this is, you are basically characterizing your data. Okay. The next step, what we often do is what is called data cleaning, right? That means the data which you have, you basically look for missing values, duplicates, you look for things like that, you clean your data, right? Then what could happen is you could actually transform your data. That means you, for example, you decide to replace some column by some other value, right? And you maybe replace it, transform it. You may group your data. For example, you have a list of employees. Maybe you group them by all the women employees, the male employees, or the employees who are earning more than a certain salary or who are younger than a certain age. So you may group your data. And then a very important feature which we use a lot in astronomy is what is called merging and joining data frames. That means you have these different data sets and you may want to merge them. For example, I have one list which is a catalog of, for example, stars, their coordinates, their distances. This is, say, from Gaia data, right? And then maybe I have another catalog which is stars, which is giving me their spectral types, right? So then I may merge these two data sets, to find out stars, their spectral types, as well as their distances. So that is what we call merging and joining. We'll see about that. We may reshape our data. We may also use with time series data. So first of all, this file is there in your GitHub. I can see that there are some people asking questions about this thing. I hope you all have the address of the GitHub repository. It has been provided to you. Otherwise, I can share it on this thing. So what happens is, okay, I'll just look for it, but I'm sure it's available with the others. So the GitHub repository has been given to you, and all these things are there sitting in the GitHub repository. So this exact file is sitting over there. The idea being that within these classes of 2 hours, we may not be able to run everything in the notebook. So then there could be things which you may run later on. Okay, fine. So what happens, like we said, like you did earlier also, when you're importing things, we often write short forms for it. For example, Pandas is often PD, Numpy is NP. So that, for example, if I'm using any of the functions in Numpy, I will have to write np dot sign, for example, or np dot mean, right? So that means Python knows where to search for the mean function. It is sitting in Numpy. So you may import various libraries. Matplotlib and Seaborn, we'll do it next time, so we'll talk more about it later. And then you could have different options. For example, if I want to list my data set, by default, when you list it, it only lists 20 columns, but I can actually say PD set option, display max column, and I write none. When I write none, it basically means it will display all the columns. I may also say display max rows. I may say my data could be in any format, but I may want it to be displayed in, in format which is 0.2f, which will be 2 decimal places. So you can actually see it like that. And then you may have a display width, etc. Right. So for example, if we are loading a data frame, let's say I have a data frame, right? So like I told you, the basic unit in Pandas is data frames. What is a data frame? It is a 2-dimensional data set where all the elements can be of different types, right? So for example, you see that this is a column, a row column thing, where there's a first column called name, second column called age, third column called city, and fourth column called salary. So name and city, these are both strings, right? The strings are name and city, while age and salary are your floats or your integers, in this case integers, right? So you can have it like this. And like I told you, I was telling you that these things are compatible. So I can make a data frame from an existing dictionary. So if I have this is a dictionary which you can see over here, name this is a dictionary. So I can convert this dictionary to a Pandas data frame, right? So I can say dfdict and pd data frame, and here inside is my dictionary. So what am I doing? I'm converting a dictionary to a data frame, right? I can even do that with a list, right? I can have a list. This is my list. I can convert that to a data frame. I can also convert a Numpy array. Say this is a Numpy array. I can convert that to a data frame. I can create a data frame myself with random values. It's very interesting to see how do systems actually create random values, right? So one of the ways of creating random values is by using a random value seed, okay? So for example, here I've put random value seed 42. So for example, even if you are going to run it on your system, right? If we both have the same seed, then we will generate the same random values. While if, for example, often the system creates random values, say from the system time or from some other sources like that, then in that case, if you and me create random values, they will be different, right? But when I'm doing it with a seed and seeing to it that both our seeds are the same, then we will create exactly the same values. So over here you can see I'm creating this thing with random value. What am I doing? These are basically 4 columns: ID, age, income, score. And in this case, this is a Numpy array, right? Therefore, in Numpy array, if you remember, everything has to have the same data type, right? That means here I cannot have a name and things like that. I am basically creating a Numpy array, and all these guys, they are not strings. They are all the same types, and I put them like this, right? I can even load external data. Supposing you get data which is a CSV file. A CSVA is a comma separated variable star. So you have a tabular data where between each line, between each this thing, I have a comma, right? So that is what is CSV, or comma separated variable. So I can actually have a file called some sample data.csv file where I input everything with commas between them, and I can make a data frame by reading it. Okay, so I can actually load external data and get this like this. So like I told you, the first thing we do is we inspect the data, we check the data. So here we are creating a larger this thing of 1,000 elements. What do? We may do various things. For example, I may look and check the data set shape, right? So it's, what is the shape? It is 1,000 rows with 8 columns. Okay, so this number of rows, number of columns. The next step I'm checking is, for example, these are the column names. It's given me the column names, and that's what I'm saying. Next is I'm asking what are the data types for each of the column. So I can write over here df large d.d types. So it's basically give me the data types for each column. These are all my 8 columns and all the 8 data types. And then I can also say head. You've already seen the head command. Default head command is 5, and therefore it's given me 5 rows. But suppose I wanted 50, I would just write 50 over here and it will give me 50. Similarly, I can look at the tail. Default, I can check it, and you see it's giving me the last 5 rows if I want some. Or I could even ask for random 5 rows. I don't want the last ones, I just want random. So I can actually say, I can say sample 5. That means it's going to randomly give me 5 rows. Okay, so I can do that. And now we can do stats in Pandas. You remember you did stats earlier with Numpy. Here, with the simplest way of doing stats in Pandas is with a command called describe. Okay, describe gives you very basic descriptive statistics for your data set, and therefore you see df large describe. What does it do in describe? It tells me the count. Count is how many rows do I have, what's the mean value, what's the standard deviation, minimum. This is the 25. Remember you all did the Q1, Q2, Q3. So this is the first quartile, second quartile, third quartile. Okay, the maximum, and it's giving me all these things, right? How many do I have? How many unique ones are there? What is this thing, and various things. Okay, so this is what we call exploratory data analysis. The exploratory, that was the word I was looking for earlier. It's called exploratory data analysis. That means you have a data set and you are kind of exploring into the characteristics of the data set. Similarly, you can also give a command called info, right? We did describe. You can also do info. What does info do? Info does similarly, it tells you that you have 1,000 rows, you have 8 columns. So by default, it gives you the number of rows, it gives you the data type, and how much of memory is used, etc. You can also look for missing values. It's possible that you have your data set. Often in astronomy, you may not have some values. Okay, so those are your missing values. And in this case, in this data set there are no missing values. Why? Because we generated this using random numbers. So everything has a number. It's not missing. So everything is there. So you can, this is your missing values. You can see all of them are 0. Another important thing is you may also look for unique values. Supposing the same name has got repeated 3 times, right? We'll see another data set where, for example, the same person is repeated 3 times. You are looking for unique values. In this case, we have 1,000 unique values, but you could have repeated values, right? So we can see that. Oh, I missed that other data set. Okay, we'll see that. Okay, next thing is you may want to actually, so now here I am going to create a messy data set. What is a messy data set? There is this data set. You can see I have name, I have age, right? I have salaries. Here in 2 cases, for 2 of them, I don't have their salaries. I have their emails. For one, I don't have the email. And then the most distinct part is a string which is called the join date, right? So this is a string which is the join date. So if you actually look at the data, this is what we'll call messy data. Why is it messy data? Because if I want to do some kind of math operation on these data, it will be difficult. Some of them may not work and some may be difficult, right? So first of all, what do? One of the standard things in astronomy data is finding missing data. So remember, like I told you, missing data was I don't have one name over here, I don't have two salaries, and I don't have one email, right? So there's one, here's a missing name, here's a missing two missing salaries and missing email. So I may look for missing values. Now in astronomy or in any data analysis, when you're doing it, one of the things that people do is if you have a row which has a missing value, you drop it. Okay. So for example, you can see over here, messy data is done. You look for where are the missing values. You print which ones are there. And what we do is you say messy data drop na. Drop na basically means you drop the row which has missing values. Okay. Now we don't, since this is just the initial part, we don't have time to talk about it. But not always is dropping missing values a good thing to do, right? For example, a very simple example was that supposing if I'm looking for the, for example, in this case, it doesn't apply to this case. But for example, if I'm looking for the number of female and male employees in this, yeah, that works. If I'm looking for the number of male and female employees in this company, right? Supposing I were to drop all the ones which have missing values. So then what happens? I will lose Bob and I will lose salary. I will lose Bob and I will use this other Bob. There are two Bobs, right? Both of them with missing salary. So what will happen is that these are two different Bobs. This Bob has an age of 130, this Bob has an age of 29. So what happens is if I was to do this counting of male female, it doesn't make me a difference what is their salary. I'm just looking for how many male employees, how many female employees. So if I were to drop these rows just because they had missing values, then my values for male and female employees will be wrong, right? And therefore what happens is I needn't have dropped this thing. So when you're dropping missing values, you have to be careful as to what are you dropping it for. And another thing is that dropping values can also lead to a bias, right? It can lead to some kind of a bias, and therefore, for example, the results you get from your data may be kind of not exactly the true ones, they'll be biased ones because you've dropped out this thing. So you have to always be careful when you're dropping missing values. So for example, here in this case, they have dropped, this is the one with salary, email and name. You can see that these are ones. So now what have they done? We have dropped the ones which have missing values. So you remember there were two which did not have, only what have we done is here instead, so we've said this thing and in place, okay. So what have we done? We're dropping the rows with missing values. So here are the ones with missing values and we therefore don't have those ones, right? You may also want to fill the missing values with something else and you may put it some other value, okay, in case you don't have. So that can also be done. You may also look for duplicates. For example, you see there were two Bobs over here, there were two Johns over here. How do we do that? So in this case, you can see is that you are looking for duplicates. You say drop duplicates, but you're saying duplicates in name, okay? Duplicates in name, and I'm saying keep the first. So you could have a John in the beginning, you could have a John later, but since we are saying keep first, you will keep the first John and not the second John, right? So depending on that, you may remove your duplicates. Another important thing is also handling invalid values. Often what happens is when we are using data, right, a lot of these data sets go through pipelines, automated pipelines, due to which you may have some other faulty values. For example, you can see over here we have Jane who has an age of -5 and you have Bob who has an age of 130. Generally, that's not the age group you will find, right? So for example, we may clip it. We may clip our data. So you can see messy data claim, clip, lower is 0 and upper is 120. That means we are going to clip off people who have ages less than 0 as well as more than 120. So Jane and Bob will get cut off. So I may actually say age clip lower 0, 120. I may also say that if I've clipped it, right, I can say apply X is if 0, I can actually replace this with 0, for example. So I may replace it with 0 and fix it. So now you see Jane has an age of 0, right? Because otherwise her age was -5. But I'm saying now that if the age, if it is lying between this range of 0 and 120, which is -5, then -5 is going to be replaced by 0. So I'm going to put 0 over here. So Jane has an age of 0. I may also clean some strings. So not only do you do cleaning for numerical data, you may also clean string data. For example, name. Maybe I may remove things before and after. I may, the email, supposing it's in uppercase, I may say string.lower, that means the string gets converted all to lowercase. So I may convert this. In this, luckily, there was nothing with uppercase, so the emails were all fine. But for example, age, if your age was not an integer, I may put it as an integer. In case you have 25.3 or whatever, it can do that. So you can do all these things. You may also select the data, filter it. So for example, here is my clean data set. I may select certain columns. For example, I may only select 2 columns, name and salary, right? I may also take it by positions, conditions. I may choose employees with salary more than 65,000 or in certain department, and I can run it like this so that I sort off my data, right? So I've sorted it my data of people who have a salary more than 65,000 or who are in IT department only. So this gives me only the IT department people, or the ages between 25 and 30. I've only selected those, or whatever. So you may accordingly choose it. You may also query, specifically you want to look for people who are younger than 28 with a salary more than 60,000. So you may opt for those. You may transform the data. For example, if with the salary you get, say, a 10% bonus. So if your original salary was 50,000, it now becomes 55,000. So I transform my data. The salary column now becomes salary per year, and it becomes 55,000, which is salary into 1.1. And therefore my new column is called salary per year is this. Similarly, I may also put age bins. I may say 0, 25, 35, 100. So if you're between 0 and 25, I may call you young. 25 to 35 will be mid. 35 to 100 will be whatever it is. Yeah, so where is it called? So it is young and mid and senior. Okay, so I may keep it in these 3 data types. I may put that. So now you see I have age, but I've created a new column called age group where I'm classifying people whether they are young or mid-age or senior. I may even apply some functions and calculate some new things, right? And use some thing. So I'm now going to leave this file for you all to have a better look at it. And instead I'm going to jump to Pandas specifically with astronomy, okay? Basically because you have those files, you all can open it and have a look at it. I am instead going to jump and specifically talk about Pandas with astronomy data sets, okay? So in general, in astronomy, what happens is we have different data sets, right? And I am an observational astronomer. I basically deal with data. And essentially when we are dealing with data and you're using Python, the safest thing is to make them all Pandas data frames, okay? So generally when I import any data, I directly convert it into a Pandas data frame because that is the most convenient way in which you can handle data, right? Like I said, this is no big rule. If you would like to put it in another format, it's fine. But so now, what are the kind of data sets? Because this is very important when you're now going to think about later on your capstone projects, which you all are going to do. You will have to think about different data sets. Okay, the capstone project which you all have to do as part of this course is you'll use a certain data set, and then you all are going to do some analysis based on that data set, right? Which will make up your project, okay? Now the data sets can be any of the data sets which are available on the net. We'll discuss those data sets in another session. But because of astronomy, the large number of ground-based and space-based telescopes, what has been done is that the astronomy data has been archived and made available to the community for people to use. It's available on the internet free of cost and for everybody. So on different websites, for example, NASA has their own website for space telescope data. So that includes Hubble space data, James Webb data, Galaxy data, Kepler data, TESS data. So there are various data sets which you can access from that. Similarly, the European ESA has their own website, and different observatories, etc., have their own websites where you have archival data. So what are the kind of data sets you could have? For example, the first one, which is described over here, is you could have star catalogs, right? Now, the most commonly used star catalog in today's time is the Gaia catalog. The Gaia is a European Space Agency satellite which was sent in 2015, and basically its job was to measure the parallaxes of 1 billion stars in our galaxy. So basically it finds out the distance, and it also measures the velocity of these stars, the proper motions in RA deck, and radial velocity for some stars. So it could be a star catalog. The second thing could be exoplanets, right? Maybe in this case, we are going to talk about a set. You're looking at an exoplanet catalog, the number of exoplanets discovered, and their analysis and stuff like that. You want to do after me, Nazar? You want to do after me?
Today.
Do you want to? Yeah. Say.
I don't have time.
Then I can give you time if you want. No? Okay. The other one is that the other data set we can talk about is galaxy properties. There's a set of galaxies for which you have their coordinates, their morphological types, etc. Then there's time series data. For example, you have a variable source. Its brightness is varying, so we have time and the variance in brightness. You could have spectral data processing. We'll talk a little bit about astronomy coordinate transformations, magnitude conversions, and things like that. So let's start off with the first one. We are just importing the libraries, and we are taking some astronomical constants. Okay, so this is exactly the same commands which we did when we started off Pandas for the PD set option, etc., and for running these things. So here we are not taking directly a Gaia catalog, we are generating an artificial data set. This is a star catalog. The star catalog has the star ID. It has the coordinates, which is RA and deck. It has the parallax, where 1 upon parallax is the distance. It has the apparent brightness in two bands, two filters, that is the V band and the B band. The spectral type of the star, the temperature, the radius, the solar masses, the BV color. So you see, this is a perfect example of this is in a Numpy array, but you can see here that we are actually, it's ideally to have as a Pandas data frame, right? So here what do we have? We have a ID, a star ID, RA deck, parallax, BV magnitudes, spectral type, temperature, radius, this thing. Okay. We are also creating another catalog, which is an exoplanet catalog. The exoplanet catalog is basically it has okay, 1 minute, star catalog is not defined. Let's run this. I'll run this first, then I'll run this. Okay, so here you can see that the catalog has as the source. This is Kepler satellite. So you can, some of you all may even opt to do a project with Kepler data. So you can, the Kepler sources are numbered Kepler 1, 2, 3, 4, etc. This is the host star. This is an exoplanet, which belongs to a host star, orbital period, and the semi-major axis. The planet radius in units of radius of the Earth, the planet mass in Jupiter masses, the discovery year and the discovery method. Okay, so the equilibrium temperature. Now, for exoplanets, we have what is called habitability, right? So typically, habitability is supposed to be if a exoplanet is at such a temperature where water is at a liquid state. So typically, you take 0 to 100. So you can see that these guys are, this one should have been habitable. Okay. Now we are also generating a galaxy catalog. A galaxy catalog has the the galaxy name, the coordinates, the redshift of the galaxy, magnitude in one band, and its morphology. Stellar mass, star formation rate, distance in megaparsecs. So here we've generated a galaxy catalog. Now, like I told you, the first thing when you have any data set is you do basic catalog statistics. So for example, here we have done print star catalog statistics. So what have we done? We've said star catalog and only these columns, not the other columns. We have picked up only the columns which have integer values or full of float values, and we are saying dot describe, right? So now you see here I have the mean, standard deviation, minimum, etc. This is, remember we already went through the dot describe command, right? That is the basic which gives descriptive statistics for the data set, right? So I can run this thing called dot describe, okay, and I get this for this. Now, if you remember in this data set, you see this was the data set. We also had what was called spectral type, right? Now, spectral type is not a number, right? So therefore, if I cannot run descriptive statistics for a spectral type because it's not a number, but I would obviously want to know what is the distribution of spectral type in my stars, right? And therefore, what I do it slightly differently. What do I do over here? I say spectral counts, right? That means I'm counting in the star catalog spectral type dot value counts sort index. So there are different indexes, right? And there are different values. If you remember, there's O, B, A, F, etc. These are the different spectral types. And therefore, what am I doing is I'm actually checking the amount of spectral types with a parameter called spectral counts. So you can see over here, I have 98 A type, 54 B type, 154 F type, 206 G, etc. So this is giving me the distribution of the different spectral types. Now this we will do next time more in detail, but you can even visualize the spectral type distribution. These are matplotlib commands. We will do this in more detail next time. But here you can see I've basically got a histogram plot of different spectral types. Here were the numbers, these are the numbers, right? And here is the distribution. For example, A type, how many do we have, etc. It's giving me the order in which the number of different stars of different spectral types. I can also use my data set to plot what is called a color magnitude diagram. Now you look at this, that this HR diagram looks very different from any other HR diagram you've seen, because basically for these stars, if you remember, all their magnitudes were taken randomly, right? So we don't have anything like a main sequence. Instead, what you see over here, these are matplotlib commands, we'll do them next time. But we basically plot a figure with BV color and V magnitude, and you're getting a plot like this. Okay, now we may want to, this is messy stars. I'm basically creating an astronomical, a messy data set, right? What is my messy data set? I have some of them which have, in this location, have a parallax of minus 999. Obviously, minus 999 parallax is not an acceptable value. Why? Because distance is 1 upon parallax. Yes. Distance is 1 upon parallax. And therefore, if your parallax is minus 999, it doesn't make sense because distance is 1 upon that. Similarly, you could have some star for which the V magnitude is not available. Then you will have a nan value written about over there. Or there could be some stars for which spectral type. So we are now adding these things to our original data set. So in location 10 to 20, all the stars have parallax minus 999. 30 to 35, these guys have no V band magnitude. 40 to 45 unknown. Temperature 50 to 55, temperature is just 0, which is impossible. And some we have 60 to 65, solar radius is minus 1. So we've added in problems in our data set, right? So what is this problem? The first problem is negative parallax, which cannot be there. This one is missing magnitude, right? This one is missing spectral type. This one is invalid temperature and invalid radius. So here what are we doing is we are going to check how many do we have negative parallax. If you remember, we've taken 10 to 20, so there are 11. Missing magnitudes 30 to 35, so there are 6. Invariant spectral types, these are 6, invariant temperature 6. Similarly, solar radius will also be 6. So these are the inserted ones which we've put in, right? Now what we have to do is we've got to clean this astronomical data, right? So when we clean this data set, how will we clean it? One problem we had was negative parallax. So for negative parallax, what do? We say cleaned with parallax is we say parallax apply x np nan if x less than 0. So for all stars which have parallax less than 0, right? Not just minus 999, but anything less than 0, we are going to write nan. That means not available, right? So we will replace that by nan because minus 999 is not an acceptable value. So I added this. For the ones which do not have V magnitude, right? Stars cleaned with this equal to stars cleaned grouped by this. We will, whatever we do is if you look over here, you can see we'll transform x, we'll fill it with x median. Whatever is the median value, we'll put that value. Okay. Then I may also put spectral type unknown. I may do this. I may fix the temperature. If the temperature is clean temperature, anything less than 2000 or more than 50,000 we will remove. So all stars which have this, so all our bad temperature ones which had temperature 0, they will all go because now we're clipping it to 2000 to 50,000. Similarly for solar radius, if you remember, the faulty ones had -1. So therefore here we are putting that, what did we put? We said clip lower 0.01. So therefore your -1 will go. That means all these will be gone. So parallax will be, it has to be greater than 0.1 and less than 100, right? So what are we doing? We are basically cleaning our data. Why do we want to clean our data? Because otherwise we won't be able to do operations on the data. For example, if we have a parallax -999, even 1, right? Then if I were to find out the mean parallax, I would get a very wrong value because I have this -999 coming in the picture, right? So therefore you have to be very careful because if you have these things lying in your data, right, then it will actually spoil the data, this thing. So when you do descriptive statistics, etc., it will all get skewed because of these wrong values, right? So therefore you need to remove these values from the thing. Hence we are going to clean it. So we cleaned our data set. You may also do some calculations. Simple, we know distance is 1 upon parallax. So I may add a new column called distance in parallax, distance in parsec, which I say is 1000 divided by parallax. Because for example, Gaia data, it is in milliarc seconds. So distance is 1 upon parallax, but the parallax is in milliarc seconds, which is 10 power minus 3. And therefore when I convert it to distance, it will be 1000 divided by parallax. I may also want to convert this parsec distance to light years. That means I multiply it into 3.26. So I will go in for light years. Similarly, I may also convert, now that I know the distance, right? I hope you are aware that for brightness of stars, it is measured at something called magnitudes. Okay. Now, obviously, the observed magnitude of a star is called its apparent magnitude. That is what it appears to me like, right? But obviously, the sun appears super bright to us because it's very close by. But you could have another star which is much brighter than the sun, but because it is further away, it looks fainter, right? And therefore in astronomy, what we do is we convert all brightness or magnitudes to what we call absolute scale. So by absolute scale, what we do is we move it to a fixed distance, and that fixed distance is 10 parsecs, okay? So how do we do that? So now all the stars which we know we have in this are all in what we call apparent magnitudes. To convert to absolute magnitude, you've got to know the true distance of the star. But since we have the parallax of the star, we know the distance. And therefore now here, this is a simple formula in astronomy with which we convert from apparent to absolute. So absolute magnitude is 5 times, this is the formula. Absolute magnitude is apparent magnitude minus 5 into log d, where the d is in parsecs, plus 5. Okay, this is the standard formula. And what we do is now we can do it because we know the small m, we know the apparent magnitude, and we know the distance. So we can calculate the absolute magnitude. Similarly, we can calculate the luminosity. What is the luminosity? If we want it in luminosity of the sun, we've just got to multiply it into ratio of the r squareds multiplied by ratio of the t power 4s, right? So I can convert the star into solar luminosity. And also, for example, I do it in this, right? So what do? I have now generated new columns, right? This is the same star ID. I've converted it in distance in parsecs. I've converted now the magnitudes all to absolute magnitudes. I've got their luminosity in solar luminosities, and I've also got their lifetimes in gigayears, right? So that this is something that we can do with the star catalog, right? Just as another example, I'll just show you this one more, and the others you can work it out yourself. Then I will give it back to sir, right? So if you take exoplanets, you saw the exoplanet data set we had. You can actually, first of all, calculate what is the stellar flux to the to the planet. What is that this thing? It will be what we know what is the semi-major axis. That means the distance of the planet from the star. And we also know what is the the star. It basically gives out your radiation, which is sigma 4 pi r squared t power 4. So we know the radius of the star and the temperature of the star. Now the radiation is coming to a distance of another distance, right? And therefore we can actually define what is the distance, and because we know the semi-major axis, so we can actually find out the stellar flux relative, which we've taken 1 upon semi-major axis squared, 1 upon d squared, right? So that will give us that. We know this distance. Only we need to remember that the d over here in the catalogs is generally given in astronomical units. One astronomical unit is 150 million kilometers, which is the distance of the Earth from the sun. We can also use the data to classify planets. So if you remember, we had the radius of the planet given, right? Now what we can do is we in radius of the Earth. So if we find that to be less than 1.25, we can say it has a terrestrial radius. If it is less than 2.5, we can call it a super Earth. Less than 6, we can call it Neptune-like. Otherwise, we call it Jupiter-like. So in our catalog, for each planet, we look at their radius and generate a new column. And for that, we talk about the planet this thing. So you get your planet type and you actually see it. We can also calculate what is called a habitability index, which will be basically, it basically depends upon the equilibrium temperature. So you check up what is the equilibrium temperature of the star, and based on that, we can actually, you can see over here, this is the temperature minus 273 divided by this, and I'm basically going to see with what is the habitability index of these exoplanets. So these are the different exoplanets. You can see it is all of them are less than 0.5. Oh, this one, yeah, everything is less than 0.5. Okay, so lesser than 50% chance, right? I won't go on to the next one because it would be kind of repetitive. Here is the galaxy data set. You can see that we have calculated, we have already had the redshift in that. We can put in Hubble's constant and calculate the distance calculated from redshift. We can again convert it to absolute magnitudes. If you remember, for the galaxies we had apparent magnitudes, we can convert it to absolute magnitudes and do things like that. So that's typically what we do with our data sets. We make it as Pandas data frames, and then first of all you explore the data, then you may actually clean the data, and then you may, for example, want to do some manipulation onto the data. Okay, so there are some more data sets described in this notebook. I urge you, the homework you'll have for this week is to basically run both the notebooks and run everything and see whether everything comes out fine. And if there's a problem, we are anyway going to meet you next week. So we'll be devoting some time for doubts which you may have when you're running the notebook. So I won't run the remaining parts of the notebook. You run it yourself and do let us know if you have issues in it, right? So I'll now hand it over to Sir again, and he can continue because he's to do some more things about stats for you all.
Yeah, hello. So I'm back again, and we'll continue from where we left. Okay, so some people were, yeah, so what we had done, if you remember, we had created some data called ages. Yeah. We took a random distribution in normal distribution centered around 35 with variance 10, and we had created ages, right? 1,000 of them. And then we had seen this pandas, we converted uh, that ages to pandas data frame. So data frame, as you notice, capital D and capital F. So you are converting ages to PD data frame and storing it in my data, right? This is what we had done earlier. And when I print it, I'm getting, there were hundreds of values. Therefore, it's showing the first 5 and last 5. And we had used this head command. So my data.head, and with default, it is giving the first 5 ones. And if you specify whatever number, if you want to just take the first 2, you put 2 there, or you put 12 there, it will give the first 12 ones, and so on. Similarly, we had tail. If you don't put any value in between, it takes a default one where it shows you the last 5. And if you want to specifically see only the last 3, you can do this. So this data frame, it has features of doing all these things. And as we proceed in examples, you see how you can make various things. For example, data frame in pandas, you also have something called concat, right? In which way I'm taking my data frame head first, say 4 values, and from the other tail, I'm taking last 15 values. So I say pd.concat, my data. So this, you have a concat is a function. So you have a round bracket, and in that you specify the 2 ranges. So when you are concatenating and you see, you are getting the first 4 of these, 0, 1, 2, 3, and last 15, right? So this is how you can do. You can pick up in between rows and other things too. Okay. Then if you want to plot this data, these ages, if you recall, uh, these are the values. And in statistics, like I said, just seeing numbers doesn't make sense. So to understand the data, there are various things. One good thing of understanding the data is by plotting it. We'll be doing plotting in detail in the next session, but some basic one which I have done in the morning in the previous session too, where we plotted a function y equal to 2x squared plus 5. We can even plot this data, which we have this my data. And if I say plt dot, see that one was plt dot plot x comma y. Here I am making a histogram of that. In Numpy also we had done dot histogram, but it was just giving the in an array form. It was just giving the data. But if you want to visualize it, somebody had asked in the question, can you plot that thing? And here it is. This is how you do it. So matplotlib.pyplot, from that there is a function called hist, and when I plt.hist my data, I get this histogram of the distribution of those 100 points which we have. Okay. And as we proceed, you will see that you can decide the bin size, and you can change the color. You can make different aspects in, but this is the most simplest way you can make a histogram of this, right? Similarly, we suppose we have uh, some other data, like we had given x equal to np dot lin space going from -10 to 10, and we want 100 values of it, right? And then I create a function which says y equal to 2 star x to the power of 3 plus 8. Okay. And if I want to do a plot of this, I do PLT dot. If I want a plot of x versus y, then I do x comma y, and I plot it. This is the function. And if you want to get the histogram of this thing, I can say PLT dot hist of whichever y or x. You are doing a histogram of that, and you are plotting the histogram of that function, right? So here we have this thing. Similarly, I can do PLT dot box plot. Yeah, in the initially I spoke about the box plot, quartile 1, quartile 2, quartile 3, and the outliers. So from the my data which we have randomly generated, if I do the PLT dot box plot, it is as simple as that, PLT dot box plot, and it gives you the box plot where this red line indicates the mean of that thing, 34.74, whatever it's coming. This is first quartile, this is second quartile, and then these are the quartile range, Q1 minus Q2. And if there were any points beyond these whiskers, then there would be the outliers. So for this data which we have got, we don't seem to have any outliers. All the data is lying well within that. So yeah, so this was one thing which I wanted to show. And these we have already done. And then we were getting into this descriptive statistics, where we have made a data set where you have ages, 39, 33, 41, 52, and so on. Then you have incomes of these people in dollars or whatever you would think. And we are attributing some scores to these ones between 0 to 100, right? And then we have randomly distributed some categories A, B, C, D, right? Random choice A, B, C, D. So suppose, okay, uh, A, B, C, D can be these people are lying in big cities, in towns, in rural areas, or in tribal areas. So A, B, C, D. So we can have some kind of a category which we have, right? It can be male, female, it can be grade A, grade B, grade C. It can be people who have taken, one can be scientists, category B can be sociologists, C, politicians, D, as technocrats, right? So these are some categories. So I'm basically, this example is to show that you can have these kind of data sets which are made up of integers, and then you have floating point and you have some categories here, some strings. Okay. And with that, we can do statistics, and we are looking at the measures of dispersion and so on. And we are getting, so we have looked at mean, median, mode, and we have seen standard deviation and variance. Then we also talked about quartile 1 and quartile 3, right? Q1, Q2, Q3. This a few more things which describes the data, which shows the skewness and the kurtosis. So skewness, it shows whether the data is uh, like in normal distribution, you have a perfect bell shape where the distribution is even, but you can have a right skewed or the left skewed data, right? So that skewness gives that. And the kurtosis gives you the tails, how whether it's a heavy tail data or not, right? So these can be very easily done in data for data frames by you have data frame dot kurtosis or data frame dot skewness. And in data frame, you notice you have square bracket incomes. So it is giving you the skewness for the column incomes. Similarly, whatever column name you specify, age if you specify, if you say data frame age here, then it would give you the skewness for age and so on. Okay, so the whole of statistics can get done very easily in Pandas, and Priya ma'am also showed you how you can do by data describe. You can get all the basic statistics just by a single command. And data profiling, you've done it, Priya. Even there's something called data profiling, and it creates the whole report. We shall do it in our next session. That's again in Pandas. It's extremely good way of getting the whole summary of your data. Okay, so maybe we should stop here. There are other things which I can do, but there are only 6 minutes left for our session. And in session 2, we'll be doing more of statistics. And I didn't want to touch upon these things because you can do, these are examples which you can see where one way of getting an histogram is plt.hist and you give it. Then it gives it. But you can make the whole histogram even more uh, beautiful and more meaningful, where you can give a legend to it, you can give a title to it. So you say set title, age distribution, and you can set X label as age and set Y label as density and so on. And you can even control the color and the line style and the line width and various things. And if you go through this, it's quite simple to understand. And what we are doing here is in the same graph, we are getting various things here, right? We are getting a whole set of histogram here, box plot here, score distribution category, QQ plot. We'll be studying what is QQ plot and category correlation matrix. All these we shall be doing later. But this block basically tells you how to have many graphs coming in the same screen. And we are specifying, for example, 0, 2, 0, 2, 0, 2. Yeah, so this is specifying the first one. And the next one is 1, 2. So it's giving you the next set of rows, right? So how many you have 1 and 2 rows, and first column and second column. That way you can get all these plots. And in the same one, we are able to define what color we want and what the histograms which we did by just did not draw the boxes around histogram. You can do it. You can control the bin size of the histogram, how large the bin and how small it is. And you can visualizing of data. For example, in this case, you can see that in this box plot, you are getting some points which are outliers. These are the outliers, and this will spoil all your statistics. And sometimes these outliers are very interesting objects which we can see. So suppose you are studying a lot of galaxies in a cluster, and most of them have similar chemical composition and details. And while some are having very little metallic content or very high, so they don't pertain to the major class of galaxies there. They are the outliers, but those outliers sometimes can be very interesting objects to study. So when we will handle some astronomy data, which we shall do next time, and we'll do all these plots again, and we'll see what these co-distributions by categories, what category distribution is. Yeah. So basically, this category distribution is how many are in the D category, how many are in B, how many. So they are being arranged in the order of maximum to minimum. Okay. So these are histograms category wise. So in each, the data which we have created, we see how many are from C, how many are from D, and counting them and creating these histograms, right? So by this kind of uh, uh, visualization, you can get a better understanding of how data is distributed. For example, you can see that in ages, the distribution is going from this the least one, and most of them are somewhere near 35, 34. This is where the mean is this is the average is coming, right? And you see this is some kind of a normal distribution which we are getting, which was randomly distributed. Median is 35, mean is 34.5. So the visualization becomes very important whenever you have data. To understand the data, you do some basic statistics to start off with, do some basic plots of that, plotting of one parameter against the other, or vice versa, and so on. And looking at the histograms will show you the distribution in each parameter space, and so on. So this will give you a very sound understanding of what the data is, and then it helps you in analyzing and understanding and making sense of these cases. So maybe I should stop with this. And if there are any questions for Priya ma'am or for me, we can answer that in the, yeah. So the time is up, and I hope things are clear to you. And if you specifically need some things you want to learn, you can write to us, and we will plan our sessions according to your requirements. And yeah, so somebody has asked, when does one require to use a box plot? Yeah, so box plot, like I told you, box plot is very good to show you where the data is like, how is it spread around the mean, where are the quartile 1, quartile 2, quartile 3 points, and the quartile range, and which are the outliers or not, which are lying within the uh, accepted limits or not, right?
That's it.
Yeah, so I think so. So we should
Hello,
stop with this. Yes.
hello.
Hello. Yes.
Yes, I want to ask a question. I I want to ask because from the first session that we had, the presenter was telling us about vibe coding. So I don't know. Um, could it be like very very much accurate and possible for us to do vibe coding in getting some of these code from AI and maybe trying to run them and they work perfectly?
Yeah. So when you want to do coding, either
He's
you can be an
asking
expert.
coding with AI.
Yeah, yeah. So coding, either you can do the coding yourself, right? Or you can use AI to do coding, right? So it is fair enough to use AI. You can use Chat GPT or DeepSeek or whichever tool you require, and it generally does a very good job. But be very careful with it, because you should not use AI as a black box. So for most things, AI is, we have seen it, and it does quite a good job. But be careful when you are using AI. And it is nothing wrong. Yeah, so we can
Yeah.
probably even.
So we will actually have a session. This is just the beginning, right? So as we progress a little bit later ahead, we will have a session where we will show you coding on Google Colab, that is with Gemini AI. Gemini is there on Google Colab. So we'll actually show you that because it's a very helpful tool to use. So we will demonstrate that to you. Yes. So we will do that.
See, like,
Oh,
there's a time when people used to compute using, writing it down, but then the calculators came and computers came and we started doing it mechanically. And there's nothing wrong in doing that. As technology progresses, one has to adapt with it. And AI, artificial intelligence, and the tools which are there, they have come to stay in our thing, and to use it candidly, use it carefully is always a good idea. And like Priya said, we will show to you how we can, actually make the AI write code for you to access Gaia data and to make something. But you always have to be very careful, because it can also give you some very false results and false things. So you have to use your human intelligence to always cross check and do. And we will do it as we progress on. We
all
will
right.
do that.
All right. Thank you, sir. Thank you, ma'am.
Good evening.
Good evening.
Can you get me?
Yeah, yes.
Okay, so I have a question on box plots. Is it
Yes.
is it always necessary to flag out outliers if you discover there are outliers in your data using box plots? Is it always necessary?
It's a good idea to use. It's always good idea to use. See, either you can find the outliers by actually calculating and doing it, right? You have to find Q1 and Q3 quartile range, and then you have Q1 minus 1.5, the interquartile range, which will give you the lower limit. Anything below that will be the outlier, and similarly, you can find the upper limit. So you can always calculate and do it, but box plot is a very simple way of doing it, and it's a very good visual representation of outliers. And statistically, those outliers which you see in box plot are statistically taken as outliers. We can't randomly decide that if you have a set of marks between 50 to 95 and suddenly one person is getting 25, he's an outlier or not. You can't decide on your own whether the person is. You have to use the statistical definition of outlier, and box plot is a very good way of getting it. It's a very simple way of doing it. It visually gives you that, and it's a good idea to use it. Yeah.
There are two more questions. Swarnabha Chanda is, how do we insert or append new data in a data frame? So that was there in the notebook. I showed you in the notebook. So please have a look at the notebook. Remember where we added more columns for salaries and stuff like that. So it's there. You have a look at the notebook and you'll see it. Santosh Kumar asked, what's the difference between bias and outliers? So outliers are values which are not, but you define the quartiles and you see whether they are outside it. For example, when you have may age -5 or age 130, these are outliers, right? Bias is a bias which you may add in your data. In your data, because of some reason, you may, maybe your missing values are for certain things. So that is a bias which you will get in your data. Okay, for example, maybe you have got data about people, but for some reason you do not have it for the older people or you don't have it for the younger people. And that's why your data will be biased towards that. So that is a different story. So that we need to be careful in our observations about the biases, right? So,
Yeah, and
yeah, you can
about the
join the
data
talk
frame.
sessions on Saturday. Okay.
And the data frames and so on will be further going into AstroPy, where we will be dealing with virtual observatory tables, VO tables, right? Those are also data frames because you can download data directly from internet in the VO table format and so on, which we shall be doing as we proceed ahead. Okay, so for today, I think we'll stop, and I hope you have understood, benefited from it, and these notebooks will be shared with you. The part which we have already done from the notebook, you can try, and things which have not been done, which we'll be covering later, you can skim through that and have a look at what it is, and yes. And yeah, with this, we'll stop for today. Thank you.
Thank you.
All right.
Bye-bye.
Thank you.